In this video, we will learn how to use Google's benchmark platform for benchmarking C++ programs. Specifically, if you write a C++ function, you're often curious about how well that function would perform and what would be its runtime. What would be its exact runtime on your own system, and then as you change the system, what would change in the runtime. So we will learn how to write test benches to accurately measure this on any system. Why using Google Benchmark, you might ask? You could instead go ahead and use a library like stdchrono, record the time before and after your function, calculate the difference, and then you're done. That would work, but my answer is that you don't want to reinvent the wheel, because Google Benchmark comes with a lot of convenient and helper functions on top of this, which would make your life easier and simplify the whole process. For example, if you want to sweep the input parameter of your function for different values, it provides a very convenient way to do this, to change the value, the input values, and then see the changes in the output over time. Moreover, if you want to estimate the complexity of your function in Big-O notation, this library does that for you. What's more, it can also calculate the coefficient of the highest term inside the runtime complexity expression in Big-O notation. And also, it can also provide the output in various formats like JSON and CSV, which you could use then to plot and visualize the runtime as you change a parameter in order to better understand how your function performs. Hello guys, welcome to this video. My name is Ari, and today I want to talk about benchmarking, specifically benchmarking C++ programs using Google's benchmark library. As you probably know, benchmarking is very important because it helps you take and make engineering decisions very accurately. So if you are having an argument with your boss or with your coworker about which approach you should take and what algorithm performs better, benchmarking is a very good way of providing some unbiased and accurate data that shows you which one actually performs better. You probably also have heard that benchmarking is notorious for being super hard, requires black magic and understanding about assembly languages and details of your CPU and a lot of other things, which is in a sense true, but at the same time, as a takeaway of this video, I would love for you guys to see that it's probably not too hard to just understand what is going on, as long as you have some basic understanding of compiler optimizations and what happens inside the cache and your memory organization. I'm actually very excited about talking about this subject. Please like this video and subscribe to my channel, and let's get started. Benchmarking a C++ program is notoriously known to be complicated. So why is benchmarking so hard? In order to understand why, we need to know that the code that you write is not exactly what's being executed. We usually write some code, then it goes through compiler. Compiler performs a lot of optimizations like reordering, loop unrolling, and a lot of other ones. Then it goes and gets executed on CPU, which itself does a lot of other optimizations on top of it. And then the CPU tries to do read or write inside cache, which does prefetching and buffering. And then does the output go inside the memory, and even memory is often organized as partially being virtual and partially being RAM. So a lot of things happen when you write your code behind the scenes, and basically it's kind of like your system is telling you, hey, you don't really know what you're talking about, and let me do some fixing and optimizations on top of what you write. These optimizations are often not observable in terms of the output of your program, the result of your program, but when it comes to runtime, they are very observable even for very simple programs. And that's why when you write your code on different systems, they might behave differently, and in a very confusing way, we may think the code might behave one way, and then when you run it on your system, you see it behaves in a very different way that you didn't even expect. Now you take the same code on a different system, it behaves completely different, and the whole thing becomes very confusing. Measuring the benchmark becomes really hard because we don't really know what happens here. So while we're not going deep inside these optimizations, it's just enough to note that they exist so that once we look at the numbers coming out of the benchmark, we don't get confused and we kind of relate them to what might have happened so that the numbers make sense to us. Now let's talk about Google Benchmark Library. This is a library that is open source and freely available. You can download it from this link. I will put it inside the description. You either have to clone this yourself and build it and install it, either using Bazel or CMake, or as an alternative, you can use my repo. I've put the link inside the description, which only requires Bazel. So you need to install Bazel first. I have a separate video on how Bazel works, which is very quick and straightforward. But once you install Bazel, all you need to do is just cloning this repo, and then after that, Bazel does everything for you. Let's see this in action. So I do git clone, the name of the repo, cpp template. Once you clone this, you will see cpp template folder created. So now I can open Visual Studio Code inside this folder. There are various folders inside this repo. All the source codes are inside source and under benchmark. So let's look at a simple example called main benchmark.cc, which basically has a function called string comparison. It takes one parameter, size. It creates two strings of the given size with this character, and then it compares them against each other. In order to benchmark this, you have to create a wrapper for Google Benchmark that takes one input parameter of type state. We will talk about what this state is later. And then you create a loop that iterates through state and then call your function with a given parameter of your choice. Once you have this wrapper, you register this wrapper as a benchmark. So now we are registering it using benchmark macro. And then this would be our main function, which again, there's a macro that replaces your main. This is now a complete executable that we can compile and build and run and measure the runtime of this. Now let's do that real quick. So I create a new terminal. It's just enough to type Bazel, run, and then the relative path to this file, source benchmark, and then the name of this file. So I just type run source benchmark and then main benchmark without .cc. So again, if you don't know how Bazel works, you're welcome to watch my other video that I talk about the details. For now, it's just enough to know that in order for this to run, you just have to type the name of the target, which is defined in the build file. I'm not going through the details, but that's how basically we run it. So before running this, also notice that we have included benchmark/benchmark.h, which is an include file inside Google's benchmark library. Now, we haven't installed or downloaded this library yet. This is done by Bazel automatically as soon as you run this command. And the reason for that is that, again, details of Bazel, but the reason for that is that inside our workspace file, we have defined Google Benchmark as a dependency. So as soon as we run this, Bazel will download Google Benchmark and provided makes it available to our executable here. So let's run this and see what happens. So now it's downloading Google Benchmark from GitHub, and now it ran the benchmark, and it looks like it took us 454 nanoseconds to do this string comparison. Now you can measure this with various different values. So let me increase the size and see what happens now. So the time goes a little bit higher. So now this is 8,374, more than a little bit. So you can see, like, as you change this parameter, the size changes and then the runtime changes, and you can accurately measure this. This output report basically gives you several information. For example, what type of system you're running on, what are your level 1 and level 2 caches, what is the load of the system, and then the final report would be under this table, the name of the benchmark, the wall time, which is 8,374, and then the CPU time, which is 8,330. So this is the actual time that the benchmark took from CPU, and then the wall time is the real time. It's the literal time that took from the time that we start and stop the execution. And there's some difference between them because there are some times for scheduling processes in the OS which are not counted in this part, but they're counted here. And then there's this number, iterations, which is the number of times that the benchmark was run. Now, before moving forward, let's review what exactly we learned here. In order to create a benchmark, you define your function, whatever that is. This is your function that you want to measure. Then you create a wrapper around it. It takes one parameter of type benchmark state. It's defined in the Google benchmark library. And then you iterate through the state, and then you call your function with the parameter that you want. Once you created this wrapper, then you register it as a benchmark. So you reference this inside benchmark macro, and then your main would be just this macro. This replaces our normal main function in C++ program. And that's it. That's how you create your benchmark. That's the structure of how, that's the main structure of Google benchmarks. Now let's briefly talk about this state parameter. Once the benchmark is run, Google benchmark runs it in multiple iterations. And based on its documentations, this is the number of iterations that it required to run it until it gets to a stable runtime. So in this case, for example, it ran it about 72,000 times. So that number of iterations correspond to this for loop here. Basically, Google's benchmark iterates through this loop as many times that it thinks it's necessary to get to a stable time measurement, and then it reports the value. Now, you can pass arguments to this function from here. So rather than having the argument here, I'm able to use this notation and pass a value of 10,000 here. So this way, I can pass it from outside to this wrapper, and then the wrapper passes it to my function. So there's one more change that we need to make here, which is state.range, and then 0 means the first parameter. So whatever you add here as an argument will go and replace to range 0, and then it will be passed to my function. So why do we do this? And that's because maybe you want to run this with different values, and that gives you an easy way of changing the parameter quickly and see the results. So let's say I want to run this for 100,000, 200,000, and maybe 400,000. So now it runs this and reports them one by one for me. So rather than modifying this several times and run it each time, I could change the parameters here and see how the runtime changes and observe it. All right, so one more time, if you want to pass a parameter, you pass it through state and state.range. So now here I'm passing this through arg, and then 1000 will be passed to range 0, and then will be passed to my function. Now, if your function has multiple parameters, then you use args, and then the first one goes to range 0, the second one goes to range 1. Not the best naming maybe for range, but that's how it is. So args with an s at the end is used for multiple parameters, and then arg without s is used for just a single parameter. If you want to sweep your input from multiple values, then you have to keep repeating this arg. So for example, here's 2 to the power 8, 2 to the power 9, 2 to the power 10. Rather than doing this, there's a shorthand of using range. So I can just say I'm modifying my first argument from 2 to the power 8 to 2 to the power 10, and then each time I want to multiply it by 10. So that's how you read this expression, which is equivalent to the first one. So we are saying sweep the first argument from 2 to the power 8 to 2 to the power of 10, and then each time multiply by 2. So you can play with these values if you want and customize it for your own use case. So let's go back to our string comparison example. So let's say let's get rid of this, and let's say I want to sweep my input value from 2 to the power 10 to 2 to the power of 20. And then each time I want to multiply the size or the input by 2. So let's run this and see what happens. You can see now the values are changing from 2 to the power 10, and then each time they're being multiplied by 2, and then for each of them I can see what the runtime was and how it grows as the size changes. Now that we learned about range, what if we have multiple inputs and we want to change multiple parameters using this range notation? In order to do that, you use ranges now. Ranges text is a container. Each member of it is a range itself. So for example, here we mean modify the first parameter from 2 to the power 8 to 2 to the power 10, and modify the second one from 1 to 5, and then each time multiply the parameters by 2. You can see in the results now that the first parameter and the second parameter are changing, and then we can observe how the runtime changes as these parameters are changing. Compile optimization flags. So far, we were able to define our benchmarks and run them and see the performance, and everything was fine. But in reality, what you want to measure is the release version, the optimized version of your program. And in order to do this, usually you have to use an optimization flag for GCC or any other compiler that you're using for your program. Usually the release version uses either -02 or -03 flag for GCC, and that's what we really need to use and compile against before measuring the benchmark. So let's see this in practice and see what happens if we go and use these flags and what happens to the performance. This is another example, which basically I wrote a function that increments a value multiple times. So it takes a parameter n and increments a value sum n times and returns the value. This is the wrapper that I wrote around it. It takes the size as an input, and this is how I register it, which basically says change the input size from 2 to the power 8 to 2 to the power 10. Now first, let's run this without optimization mode. So using Bazel, I can just run Bazel run source benchmark, and the name of this file is main benchmark adder, no extensions. All right, here are the values. Now let's compile this again, and now give it the optimized flag. So in this case, for Bazel, I can do optimized flags with -c opt. As soon as we use the release version, now you can see the times that takes to do these calculations is 0. So this is a little bit surprising and confusing. But knowing that we are using the optimized version of the code, you can probably guess that this increment, because the compiler knew what the value, the parameter of it is, it could at compile time guess, or I should say exactly calculate the result of the increment with any of these parameters. So it actually reduced it to a constant. So basically the whole incrementing of this loop for 2 to the power of 8, that would be 256. So the result of this would be reduced to 256. And that's what the compiler did. And that's why we're observing these 0 values. So as I mentioned in the beginning, benchmarking is hard and it can be confusing because of these surprising results. And in order to make some sense out of them, you have to know that there's optimization in the compiler, there's optimization in CPUs, and there's also optimization in cache and memory. Once you know that, then you can kind of relate these numbers and kind of guess what made them to become 0 and what to something that you didn't expect. Now, in order to prove this, you probably have to see the assembly code, the compile code, analyze that, and see what happened there, which I don't go over that part now, but we can be very confident that this is what the compiler is doing. Now, you observe that these are the flags for GCC, and for Bazel, I use another flag, which was -C. So for Bazel, you can use -C or -- compilation mode, and it takes three values. It's either fast build, which is default, or debug, which adds the debug information, and OPT, which is the optimized version, which is equivalent to -O2 of GCC. Now, if you want to specify the exact flag that goes to GCC, you can use --C OPT flag for Bazel. So basically what I'm saying is that we use Bazel run, and then we gave it this -C opt, which is equivalent to -O2. But if I wanted to go to -O3, then I could use -C opt is equal. This means give whatever I put here to GCC. So basically from Bazel, you can sort of give parameters to GCC if you want to. Now, what if we do actually want to test our release version, but we don't want to optimize out for a specific part of the code? In order to do that, Google Benchmarks framework provides two functions, which are do not optimize and clubber memory. So in this increment function, I can say do not optimize sum. That means it forces the result to be stored in either memory or a register. That means because we specify this, the compiler won't be able to optimize and short circuit the whole thing to a constant. And this one, clubber memory, it forces the compiler to perform all pending writes to global memory. So it might be the case that it increments the sum, but it goes inside cache. But if you actually want to see what would happen if you go all the way to memory, use the clubber memory function here. And then this way we can measure the performance of this specific function. We still use release and optimize compile, except for this line that we don't want this sub to be optimized and the whole thing gets short-circuited. Now let's see this in action. So basically, instead of having sum here, I say do not optimize sum, and then we do clubber memory. Now let's run this and see what happens. So we see non-zero numbers, although the code was optimized and used the optimized flag. And that's probably what you want to do as you measure the performance of your code. So if you're doing serious benchmarking, I will encourage you to go inside the source code of the Google's benchmark framework and make sure you understand what exactly these functions are doing. Now, the other feature that this library provides is pausing and resuming the timer. So let's say I have this benchmark, and this is the function that I want to measure, ternary search. And let's say I want to first prepare data here, and then after that measure my function. But I don't want the timer to account for the time that I spent inside this initialization function. So to do this, basically this state provides two methods, pause timing and resume timing. So basically all you're saying here is that let's pause the timer, let's initialize the data, and then resume the timer. At this point, we are accounting that all the time that's being accounted for is just for ternary search and not this initialization. Measuring runtime complexity. So let's say I have a function here called ternary search, and I want to know what's the runtime complexity of this function. So what you need to do is basically inside the wrapper add this call, which is set complexity n. It has to get as a parameter the size of the problem. For example, if your array is of size n, this should represent n. And then inside where you register this as a benchmark, you add complexity, and then you can either give this parameter to it so that it knows the complexity is already O log of n. Therefore, it only calculates the coefficient of the highest term in the runtime complexity expression. Or if you leave this free, it tries to guess and fit in what it thinks the complexity of this problem is. I will show you guys an example of how this can be used with some surprising or maybe interesting results, and let's get to it. So let's see as an example how good binary search is. Binary search is a really well-known algorithm, very popular one and very effective, that we all know and love and think it's one of the very fastest and most efficient algorithms. Now the question is, can we find something better, or how good this binary search algorithm is really in practice? So we know in binary search an array is given and we want to know if a certain element, if a certain value exists in this array or not, and the array is sorted. So the way it works is that it cuts the array into two pieces, and then it compares the input to the midpoint. If it's greater, it searches the right side. If it's lower, it searches the left part. So here we cut it to two pieces, then we search the right side recursively, and then again we look at the midpoint. If it's greater, we cut the array again, and then we search in the right side until we find the value. Because we are dividing the array into two each time, the runtime complexity of this is log n in base 2. Since we did binary search, why not doing ternary search? Meaning each time divide the array into 3 pieces, and then each time look and see if the value is in this cut or in this cut or in this cut, using 2 middle points now. So once you do this, you can probably get, or I should say you definitely get to the answer faster, because now you are doing log n in base 3 rather than log n in base 2. But then the question is how these algorithms are different in practice. Now, another optimization is multi-threading binary search. So I could go ahead and do binary search inside this array, but another approach is to cut this into m pieces, m. So here I have 1, 2, 3, 4, 5 pieces, and then I run binary search inside each cut separately in a separate thread. So in this case, each thread will run in log n by m base 2. Now the question is how better this would be in practice compared to normal binary search. Another alternative would be exponential search. In exponential search, first we run a search through the array and we compare the element that we are searching for with indices 1, then 2, then 4, then 8, and then each time we multiply the index by 2. As soon as we see the value we are looking for is less than the value in the index of these jumps, then we stop the search and then we look between the last 2 jumps. So between, for example, here, between 4 and 8. Now we run the simple binary search inside this array rather than this big one. This has the runtime complexity of O log I being the index of the element that we are searching, for example, number 7, rather than O log n in base 2. So O log I base 2 rather than O log n base 2. So it can be slightly faster, but we want to know how fast it would be in practice. And we expect this to be faster for indices that are in the lower part of the array than the higher part, because in that case, this array would be very small. For your reference, this is the source code for exponential search. I'm not going through the details. It's the same thing that I explained. So here is where we did the initial search and then we do the normal binary search. Now, let's see this in practice. If you want to run all of this different flavors of search in a sorted array and see which one is better, I already put inside lib search cc and search h. So in search, so there's binary search, ternary search, exponential search, and binary search parallel. And in order to run this, I wrote a benchmark. It's under source benchmark, main benchmark search, which basically instantiates these different searches and tries to find their complexity and the highest term in the complexity expression. So running this would be Bazel run source benchmark main benchmark search, and then we run it with -c optimize. So once you run this, you see the results. For example, for binary search, we do see that the increase, as we increase the size, is kind of similar to what we expected, as in log n, and then this library calculated the coefficient of the highest term in the runtime complexity expression. The same thing for ternary search. So you can see that between ternary search and binary search, there's not really that much of difference. We just go from 125 to 124. And that's why ternary search is not considered a super alternative and much better alternative to binary search. So as you can see in practice, the gain that we get is not really that high. With exponential search, it actually goes higher, and the reason for this is that it goes slightly higher. The reason for this is that we were searching for the last item in the array, which is expected to have a higher runtime compared to the normal binary search. I will show you guys the alternative when we search in the lowest part of the array compared to this. And this last one shows the multi-threaded binary search. As you can see, there's a huge jump from these numbers 1910 to 28,000, which shows the overhead of just creating threads compared to having a single threaded binary search. So looks like, at least the way I implemented them, and you're welcome to look at them and modify them as you wish, binary search is still a really good alternative, and maybe ternary search is very close, and exponential search is not that much better. But now let's see what happens when we look for lower indices. So in this case, we are searching for something around index 100 in the total of 32, 768, and so forth. So in this case, compared to binary search, you can see exponential search does a little bit better, but it's still not that much. So from 154 on this coefficient, we go to 152. So that means a little bit of gain, but it's really not that much. The timing is 2251 compared to 2229, only about 20 nanosecond difference. So if someone asked you if binary search is a really good and efficient algorithm, the answer is probably yes. And the alternatives that we have are not that much better. Unless you do some sort of hashing or other fancy stuff, binary search is the way to go. One last thing before I wrap things up is to bring your attention to pay attention to numbers. So here, as I was changing the values, the input size of the binary search algorithm, everything was working until this point. But as soon as I double the size of the input and I go to this value, I see a higher jump. So from 22, we go to 67. So now this is 3 times more. It's not log of n anymore. And then I go to the next one. Again, I double the size of the input, but the runtime kind of explodes and it gets really, really high. And then the coefficient that the benchmark calculates for us is really high compared to what we calculated before, which was only seeing these few items in the beginning. And that is very puzzling. Again, that is very surprising. It's not what we expected. We expect binary search to grow in a logarithmic way rather than these huge jumps, and then after that it's doing like sort of in a linear way rather than logarithmic way. So one thing that I want to say is to make sure you pay attention to these numbers as you do your benchmarks. And in this case, maybe, and I leave that to you if you want to experiment on your own system, but maybe this has something to do with the values of the cache. So it looks like maybe this is around the time that we start getting a lot of cache misses, and the time that we go to actually bring the stuff from the actual memory rather than the cache is really high. The overhead is really high. Then most of the time of the algorithm spends in that part rather than the binary search itself. So we don't really see the effect of binary search, and the time that we spend to fetch memory stuff is much more. And what we're seeing is actually that time, not the time of the binary search. So again, pay attention to the numbers. Look at your cache value. You should be aware of your system, and then you should also be able to interpret and find out why these numbers are changing like this. Like I said, if you're doing serious benchmarking, you probably have to actually go inside the assembly code and find out what exactly is happening. But as long as you know a little bit about your cache, about your compiler, and the flags that are turned on, it's probably enough just to make a very educated guess and know what is happening here. Summary and ending notes. So we talked about Google Benchmark. It's a free library that allows you to do your benchmarking in a very efficient way. It allows you to do sweeping parameters, do pause and resume the timer in a very easy way. Although you could do all of these things yourself, again, this is something that these are just convenient functions, make your life easier, so probably it's better to use them rather than reinventing the wheel. Benchmarking, it's very important to know and have a careful understanding and do a careful analysis of your entire system to understand what exactly is happening and what the numbers are. And for critical programs, now that you have this tool, try to always benchmark and find out what works best for you. That's it, guys. I really enjoyed talking today. Thanks for watching this video. Please make sure to subscribe and like this video. And if you have any question, post it in the comments. I'll be happy to answer. I'll see you guys in the next ones.